you're planning on going into data analysis or anything like that, that's where they're pretty useful. So you got extremely large numbers, maybe like a national debt type numbers that large. Breaking them down into using logs to make them smaller numbers that are easier for your computer and you to manage. That's what they're useful for. So I don't feel like you'll probably use these very much in life, but they are pretty easy to do. So we're going to work our way through here. So the first thing that we're going to be working at is taking a logarithm and rewriting it as an exponential statement. And then we're going to go the other direction. We're taking an exponential statement and rewriting it as a log. And they have the same components. They're just in different locations. Okay, so for this, anything with this has a laser on it. It doesn't. The base, we have when you read this, this is log base b of some number is equal to x. The base that's the log is the base of the exponential. And when we say base on it, what's the base? 3 to the x or something like that. The base is 3. The base of the exponential is the same as the base on the log. And then what it's equal to on the log is the exponent. That's where I get the logs are just exponents. Logarithms are just exponents, meaning logarithms are equal to exponents. So base is here, exponent's there. Base, exponent, what it's equal to, just different, okay? So we're going to work on rewriting that. What that's useful for is when we go to solve some equations pretty quickly after this, we'll solve some equations. And some of them you want to rewrite them as logs because it makes them easier to solve. Some of them you want to rewrite them as exponentials because it makes them easier to solve. So one of the tools of a good mathematician is being able to make something look like something that's easy. You can make it look like something you already know about, makes it easier, right? So you ever solved a Rubik's Cube? If you've ever messed with those, if you look up online how to do it, it tells you to get it to a certain pattern first, and then it tells you where to go from there. What they do is they move it around until it looks like something familiar, and then they know everybody's starting at the same spot. So if we do these things, it'll solve itself. Okay, so that's what we're going to be working on doing, is getting something to rearrange itself into something we know how to do, or makes it easier to do. Maybe we don't know how to do it every situation, but a lot of them we do. So we're going to work on rewriting some stuff first, and then we'll use that in solving some equations with these things. So we're going to start out with logs, and we're going to rewrite them as exponentials. So the first one, excuse me, is log base 3 of 81 is equal to 4. So if we're going to rewrite that as an exponential, remember, whatever the base on the log is the base of our exponential. So this will be 3 to the 4th power is equal to 81. We're just rewriting it. We're not really doing any calculations or anything right now. We're just rewriting it as an exponential. Okay? So the base of the log is the base of the exponential. What the log's equal to is the exponent. So example B, we have log base 2 of 8 is equal to 3. So what would that one be? Yeah, well, that's supposed to be a 2. Sorry. My handwriting's not real great. But 2 to the 3rd is equal to 8. Example C. Good job. That's it. Example D. What's the base? 6, because it's log base 6 of 1 is equal to 0. So 0 is the exponent. 1 is what it's equal to. 6 to the 0 power equals 1. Every one of these that you swap, what they're doing, they should be a true statement. You'd be able to calculate and determine if that's true or not. 6 to the 0 power is 1. Now, here's where it gets a little bit different. Is ln, that's ln, natural log is what that stands for, of 6 is equal to y. And this is a little bit different. natural log, ln, is log base e. And if you look on your graphing calculator, down the left-hand side there, if you look at that, there's a button. It's the third one up from the bottom, right there. I'll make it turn red. That's the natural log. It happens so often. It's what's called a common log. It's used enough in using logarithms and in science classes and various things like that it got its own button on the calculator. Log base E is what it stands for, though. Log with an E as the base. E is just a number. It's e to the first power is not 1 point, but 2.71 and some change, a bunch of decimals after that. It's kind of like pi. It represents a number. It's just a symbol that represents a number. It's the letter E. Why they chose E and not F or Q or some other number or letter, I don't know. But they picked E. And I guess because it's exponential, and they picked the E for that. I don't know. I'm making that up. I don't know. You could Google it. I'm sure there's somebody that's got an explanation. It's a lot smarter than me. But log base E. So when you see that, you're going to think this. They're not ever going to write it that way. They're always going to write natural log, ln. But think, oh, that's log base E. That's all that means. So that would be E to the Y is equal to 6. That's all that means. That's converting over. Okay. So natural log is log base E. And go from there. All right, so let's go the other direction. We're going to take exponentials and rewrite them as logs. So remember, whatever the base is on the exponential is the base of your log. Okay, so when you look at this one, what's the base on example F? 5. So it's going to be log base 5 of 1 over 125 is equal to the exponent negative 3. Okay, and maybe some highlighting helps, unless you're colorblind, and then it's useless. So that's where all those things are coming from. Log base 5, what it's equal to is the exponent. What it's of is the number that the exponential is equal to. All right, this one's a little weird. It looks weird because it's 12 to the first power is equal to 12. But what's the base? 12. So that would be log base 12 of 12 equals 1. Okay. That's an interesting property that we'll engage in later. H, what's our log base? 10. Of 1,000 equal to 3. Now, notice that I did not write a 10 down there. This is one of those common log things again. This is like the natural log was with the E. The number system that we live in is a base 10 number system. That when you're looking at a number like the number 346, that's really 3 times 10 to the second power plus 4 times 10 to the first power plus 6 times 10 to the 0 power. That's how we build numbers in our world. And I just unplugged my computer. Plug it right here. Sorry about that. There we go. That's how we build numbers in the world we live in. Base 10. That's the 100. 10 to the second power is 100, so that's 300. That's 300. The 100th digit. 10 to the first is 10. That's the 10th digit. 10 to the 0 is 1. That's the 1's digit. That's how we build numbers in the world we live in. Okay. If we lived in a different society, different time, or if we only dealt with electronics, we might live in a base 2 number system, binary number system. But we live in a base 10 system. So log with nothing written there is a base 10. Okay. It's got its own button on the calculator. It's used, we live in a base 10 world. If you press that button, it's red there right beside the 7 on the graphing calculator. It's the log button. It's log base 10 because it's a common log. We live in a world where base 10 is normal. So log base 10 is what we use. There have been societies that did a different number system that wasn't base 10. They didn't last very long. I don't know why. But because they couldn't count. They counted differently than we did. But base 10 is how we live in this world. So regular log is log base 10. Okay, so just remember that. It'll come in handy later. All right. Example I, e to the fourth power is equal to y. So the base is e. So that means what log are we using? It's the ln. ln of y is equal to 4. Remember? Whatever the exponent is what the log is equal to. So natural log of y is equal to 4. Natural log of y. Okay. All right, so where's this useful? What are we using it for? Let's solve some equations. We'll see where it's useful. All right. Example J. Solve. Log base x of 16 over 9 is equal to 2. Okay, so here's a logarithmic statement. I don't know a whole lot about log base x, but I do know some stuff about rewriting logs as exponentials. That looks weird because it's log base x. That's not even a base number. But if I rewrite it as an exponential, maybe it makes sense. So that would be x to the second power is equal to 16 over 9. That looks a little bit more familiar, as in something I know how to solve. How do I solve that? How do I get rid of the squared? No, I can't divide by a square. Square root is the opposite of squaring. So if I take the square root of both sides, don't forget the plus or minus, and then I simplify that square root. What's the square root of 16? What's the square root of 9? 3. So that's 4 over 3. There's my answers. So I took that log equation that looked weird and rewrote it as something that I've solved equations like that before. So that's what I'm thinking here is that can I rewrite it and use something I know how to do? Like, for example, here's another one, log base 16. So this one does have a number as a base of x is equal to 3/4. Well, that's fun. Rational exponents. Because I don't know a whole lot about log base 16, but I do know how to rewrite that as an exponential. That I could rewrite that as the base of what? 16 to what power is equal to x? Hey, that's already got x by itself. All I got to do is work out what 16 to the 3/4 power is. What do I know about 16? I know 16 is 2 to the 4th power. And then what do I do with these two exponents? Multiply. Well, that'd be 2 to the 3rd. And what's 2 to the 3rd power? X is equal to 8. I'm going to unplug this thing again. I keep bumping this cable here. So we're taking something that looks unfamiliar and rewriting it into something that we've done before. Maybe it doesn't feel as familiar as it should, but it does work out really nice. Let's do this one. Log base 36 of the square root of 6 equals x. This one's real weird. Okay, that's a good start. Is equal to what? Square root of 6. Now, I don't know a whole lot about undoing the 36 to the x power. Here we got an x in the exponent. The variable is an exponent. So what I would think about doing is maybe rewriting that so that we have the same base on each side. Because on the right side, square root of 6 is the same thing as 6 to what power? 1/2. 36 is 6 to what power? 6 squared. So that's actually 6 to the 2x over there. And now that the bases are the same, what's that mean about the exponents? They should be equal to each other, right? If I've got an equation set up where it has 6 to some exponent is equal to 6 to 1/2, well, the exponent on the left side should be equal to the exponent on the right side, right? It make logical sense that it should do that. So that'd be 2x is equal to 1/2. And how do I get x by itself now? Divided by 2. 1/2 divided by 2. Half of a half. A fourth. Good job. I asked that in high school and they go, huh? What? You can't have a half. It's already a half. Bro, you can't have a half. They say that all the time. I don't understand. All right. Log base 4 this time of x is equal to 5/2. Be a little bit easier on this one, but the fraction exponents make it a little tougher. How could I rewrite that as an exponential? 4 to the 5/2. Okay, so that's 2 squared to the 5/2. And then those two multiply together, right? That's 2 to the 5th. What's 2 to the 5th power? 32. Got it. Example N. Log base square root of 7 of 49 is equal to x. Okay. All right, so we got to think, okay, what do I know about 49 and then the square root of 7? Yeah, so that's really 7 squared then, right? So the left side could be turned into 7 to the... What power does this turn into? Square root turn half. 1/2 x. So now the bases are the same again. And if the bases are the same, then the exponents should be equal to one another. 4.
So first you're saying 7 to the 1/2 x is the same thing as the square root of 7.
Yes, that's exactly what we're saying. Yes. We're saying that the square root of 7 to the x power.
This is a different way of saying this.
Perfectly. That is exactly what we're trying to do. Exactly what we're trying to do. All right. Got a little cheat sheet for you here. So you don't have to write these down all individually. So that you can use these to help you do the next set of problems. Properties of logarithms. I went ahead and included properties of exponents up there at the top. And then if you look there at the inverse properties, that third line, that's what we've been employing here so far. Been doing that already. So the next thing we're going to look at is some product rules, some quotient rules, some power rules with the logarithmic things. All right, so we're going to look at doing that. Expanding expression is what it's called. Okay, and we're going to, again, we're using these we're learning these little properties and rules that we can use to help us later on solve equations. That's the end goal of all of this stuff, is we're going to solve an equation using these rules, is what we do. So we're going to expand the logarithmic expression. So we're going to expand first, and then we'll condense, and then we'll use that to maybe solve some equations. That's the order we're going in here. No idea what letter we did last. N. So example, donut. All right. Log base 7 of 8 times 6. All right. So here, we're not trying to evaluate anything here. We're just working on skills of expanding a log. What's going on the inside of the log between the 8 and the 6? Multiplication. That's what's that called? A product, a quotient, or a power? Product. So we're looking at the product rule. What does a multiplication turn into with logs? Addition. Think about what I said at the beginning. Logarithms are just exponents. What's the rule when you multiply things with the same base? What do you do with their exponents? You add. Logarithms are exponents. So when you're multiplying, the rule for exponents is add. So when you're multiplying in a log, it's an exponent. So the rule is you can add. So what we do is we split this apart. We expand it so that it's an addition problem then. So this becomes log base 7 of 8 plus log base 7 of 6. And we've expanded that statement. Addition becomes, or multiplication becomes addition when we're expanding. Example P. Log base 6 of 3x. What's going on inside of the log? Multiplication. Multiplication becomes addition. So it just takes log base 6 of 3, log base 6 of x. All right, so expand this one. What's going on inside of the log? Division. Division becomes subtraction, because the rule is when you divide things with exponents, you subtract exponents, right? So log 15 minus log 7. What base are we dealing with here? 10. Good job. Okay. Doesn't really matter what base you're dealing with on this because we're just expanding, but when we go to solve, it would matter. It's a common log of 10. That if there's nothing written there, it's base 10. If it's anything different, they'll write it there. Base 10 number system we live in, plain log is the common log, base 10. All right. I won't count off any if you write the 10 there. That's fine with me, but you just won't see it written there usually in a book or on test or quiz or anything. Okay. All right. R. Log base 3 of 27 over x. How does that expand? Remember, it's always going to be top minus bottom. Very easy to expand there. So division becomes subtraction. Multiplication becomes addition. Log base 2 of x squared. This is where we got maybe something different going on. Now, is that addition or is that multiplication, division, or power? Power. So let's look at the power rule on our little handout here. What happens to the exponent? Where does it move to? The front. The reason it moves to the front is, remember, with exponent rules, when you had something like, x to the third squared, you multiplied exponents, right? So by moving it to the front, that's like saying 2 times the log of it, base 2 of x. That's what you're doing there. That's the exponent rule that's related to. Okay. So exponent moves to the front. T. Log base 3 of the cubed root of x squared. Now this one's a little bit more difficult. Stepping it up a little as we go here. Let's think about what we did with radicals and how we could rewrite radicals as exponents. That's the key. It'd be to the what? 2/3. That's right. So this is really log base 3 of x to the 2/3. And then we can employ the power rule. We don't have a rule for radicals. We have a power rule. So that 2/3 comes out to the front. And it's log base 3 of x. We're going to kind of remember, hey, this is exponent rule. So we need to rewrite things as exponents. So we had log base 4 of x squared, 4th root of y to the 3rd. So stepping it up a lot here. Putting a couple of things in there. So that turns into y to the 3/4. Good. So this is log base 4 of x squared, y to the 3/4. All right. So we're taking the log of all of that. What's going on between all of that? So I need to turn that into addition. Log base 4 of x squared plus log base 4 of y to the 3/4. So I'm taking this one step at a time, and if you see more than one rule that you can apply at once, do it. I'm just trying to do it one step at a time as we're learning. Now, can those be expanded a little bit further? How? The power rule. So what happens to this first one? Good. There you go. And we've expanded that out as far as it'll go. Yes, we will. We're about to do that. We got one more example of expanding, and then actually 2 more examples of expanding, and then we're going to condense.
It's all one lesson.
Huh?
Oh, man.
Condensing is better, like Campbell's soup, condensed soup. Log base 7 of x over y to the 5th. That's a v, sorry. Is that better? Does everybody have that exponent? No, then I can't bring it out first. I need to do subtraction first because everybody is involved in the division. So I can do log base 7 of x minus log base 7 of y to the fifth. Now I can bring that exponent out. And it's only on the y to the fifth. Yeah, so the first one's going to stay the same. Good. And then we have 5 log base 7 of y that we're subtracting from that. And after you've done several of these, you'll get to where you do more than one step at once. Most of you will. You're like, oh, well, that 5's going to come to the front anyway. I'll just go ahead and do it. That sort of thing. Log base 8 x y squared z over w to the third b to the fifth. I'm trying to find some letters. Lots going on in this one.
Okay, so that'd be division.
Yeah, the first thing we're going to do is subtraction. So log base 8 of x y squared z minus log base 8 of w to the third v to the fifth. I'm not combining anything. Remember, I'm expanding, so I want to break apart anything. So let's get the first part here, the log base 8 of x y squared z. How does that break apart?
You have to, I mean, that takes the multiplication.
Is it multiplication in there when they're mashed together like that?
I mean, no.
I'm asking.
Yeah.
Yes, it is. Yeah. So multiplication turns into addition. So that first part's going to all be addition. So log base 8 of x plus, what can I do with the y squared? What moves to the front? The 2 can move to the front. So I get log base 8 of y. 2 log base 8 of y plus log base 8 of z. I wrote too big. There we go. Now, I'm subtracting everything after that. Okay? It's very important that you realize that everything after that is subtracted because this minus sign is on all of that.
You do it to like write it like you're adding.
Yes, that would be how I would do that. Yeah, so it'd be log base 8, or what does the w cubed turn into? 3w, and then another minus because I'm subtracting all of that. 5. Yeah. And we've expanded that all the way there. Okay. All right. You need to take a break real quick? All right. We'll do another one of these while you're gone. Because we're going to get to Z, and so that's awesome. So. WX. Example X. Let's do log base 2 of, it looks like a Z, let's make it a 2, of 8 x to the fourth y squared over 7 w z to the third. A little bit even more involved there. All right. Let's expand that. So, top part, log base 2, 8x to the fourth, y squared, minus log base 2 7wz to the third. All right. What's it gonna be?
So it'll be
I'm waiting. Go ahead.
the 4 log base 2 x.
You're missing something at the beginning. What should happen? What should be at the very front? That for the piece you're talking about. That's right. But what about that 8? What happened to it? No.
Okay, so is the 4 right 4 log base
2 of x. That's what you said. That's
8x?
No.
No.
the 8. Does the 8 have the exponent?
No.
No, only the x does. Log base 2 of 8 plus the 4 log base 2 of x plus, and then what's the y part go to? This 8 doesn't have an exponent. So you can't combine it and have 8x. That's not 8x to the fourth, it's 8 times x to the fourth. So that's why I've got log base 2 of 8 in the front, and then the 4 log base 2 of x. And what's the y become?
2 log base 2 y.
Mm-hmm. Now let's see if we can take that and go with it for the second half. Log base 2 of
7.
We've expanded everything that could be expanded.
Really, as long as you just stay calm. Don't panic. You're good.
Yeah, sir.
I got you.
Yes, sir.
No, no. Oh, really? That's exactly
Division, yeah.
One of them, you take the numerator and break it down. Subtraction and number.
Uh-huh.
Then, what you got highlighted in the green part, you explain your.
I'm breaking apart the numerator part and then breaking apart the denominator part. So like here we're breaking apart the numerator.
Okay,
This one. So it's the same kind of idea as the previous one. And then denominator is this part.
All right.
So what I've written in blue is the expansion of this.
Okay.
Okay? And then what's written in green here is the expansion of this, but just minus signs in front of it because it was all from the denominator. Okay? So log base 2 is 7. That's from here. W is from here, from the denominator. The 3 log base 2 of z is from the denominator. So it's all these are the minus signs. So I'm splitting it apart first with the division, and then I'm splitting apart with the product rule after that. So product and so I'm using every rule that we've talked about is used in this problem.
So what happens in the first expanse carries on in the second expanse?
Yes. It's like a tournament bracket. You know, it just keeps. You know, you want 2 teams at the end, it splits apart. Okay. All right. Let's condense, and I think this is where you start really getting good at the rules. Condense. All right, so what we're going to do is we're going to condense these into one single logarithmic expression. So it's going to start out on example y. as log base 4 of x minus log base 4 of y. And let's just start with something easy like that. Since that's subtraction, that means that came from what? Division. So what got divided? X. Yeah. Front by back. You condense that to one log. Simple Z. All right. 3 log base 2 of x plus 4 log base 2 of y minus log base 2 of w. So what operations do we have going on here? Okay. So we can do it step at a time. That's fine. Let's do log base 2 of x cubed plus, and then what does this second one turn into? Okay, so that's undoing the power rule. That's what she's doing there. No power rule to undo on this last piece. Okay. Now what? Okay, so what gets multiplied? Nothing happening with the second one yet. Now what happens? All that over W. That's right. And there we've condensed it to one log. That's one step at a time. And that's quite okay. That's perfectly fine way to do it. One step at a time. I tend to get a little impatient and try to do more than one step at once. All right. Example AA. 4 log base 7 of R minus 5 log base 7 of X. See if we can throw this one in one step. Okay. That's it. In one step. Good job. Yeah, it's like a puzzle.
It is.
Sydney, I'd love to tell you that this is going to make you better at playing guitar, but it's not. It's going to make you enjoy playing guitar more. All right. A little bit more. Mm-hmm. Okay.
And then over,
Okay. Or cubed root is the same, or as the same as the denominator of 3. So you might see it written like this. That's the same thing. Take the denominator and make it the index on the root. You might see it written both of those ways. Yeah, sure. If you can do those, you're good. You're fine. You're not going to have a whole lot of trouble. Okay? All right. Let's take a break from the hard stuff and do some easy stuff for a second. Okay? I know it gets pretty intense for a second. Let's evaluate with a calculator. Don't get much easier than that, right? Log of 49. With the calculator, log of 49, you're just going to hit that log button on the left side of 49. Because it doesn't have a base written there, then we know it's base 10. And we're going to go, let's go 4 decimal places. So 1.6902. Log base 2, 15. We're going to approximate that with the calculator. All right, to get a log base, a couple of different ways to do it. We're going to do use the function log base first, and then I'll show you the change of base formula that you can use if for a chance you don't want to go this route. So hit math, and you'll press the up arrow. You're looking for a thing that says log base, LOGBASE. Hit enter, and you should have a box that shows up here. It's log base 2, and then of what number, put that in the parentheses. If yours does not do that, then you're going to do it the next way I'm going to show you. It gets you the exact same answer. And sometimes I do it this other way just because it's quicker. And hit enter. Going 4 decimal places, so that'd be 3.9069. All right, the other way would be do log of 15 divided by log of 2. Using that log button that's on their calculator there. So log of 15 divided by log of 2. Make sure you close your parentheses on the one that's on top. If you don't, it'll be wrong. And you notice it's the exact same number. So it's about the same number of keystrokes either way, which is why I use that sometimes too. I can't remember exactly what year it was that they put that log-based function into the new operating system on the graphic calculators. It's not been too distant past that happened, that they did that. So I've kind of been used to doing it that way for a long time. So either way of those, works there. Whatever your base is goes on the bottom as the log, and then whatever you're taking the log of is the top every time there. It even works if you forget and press the LN button. Whoops, not store, but LN. Gets you the exact same answer. You can't screw it up. As long as you type it in the right order, you can't screw it up. All right. So that's evaluating with the calculator. All right. Now, all of that stuff, that's a big section, is to help us with the next 2 or next 3 sections. Okay. And then that's in evaluating and then working out and solving some equations as we go here out of that. So let's get to section 4.4. And I want to cover these types of problems. We don't do a whole lot out of section 4.4. It's applications of logs. They're good for building homes with. You slice them just right. That's a joke. I'll get that. You're getting bored, so I thought I'd throw something in there. All right. You nursing people might need this. I don't know. I don't know what you do in nursing other than just clean up people's junk. So, all right. pH levels. Anybody got a pool? You got to check the pH. You got chlorine in it. You got to check the pH and all that stuff in it. It's no fun. Salt water's a little easier to maintain, even though it, you can still get pink eye from that. So. All right. So pH level is the level of the H3o ion in there. I can't remember how that's called in chemistry, but anyway, it uses a logarithm to calculate that. So what we're going to be looking for is finding the pH level, and then going in reverse. If we have the pH level, how do we get the concentration of that ion in the water or whatever liquid it is or substance that we're testing? How do we go from there? So let's look at some applications that we're going to find the pH. You might know what pH is. I remember that from high school. It's the level of acidity in something. So when the concentration of the ion is 2.5 times 10 to the negative 4, I guess molecules of H3O. If it's that, what's the pH? So pH is equal to the negative log of that number. So this is one of those easy things. Evaluate with the calculator problems. And we're going to approximate that to a pH level. So I'm doing negative log 2.5 times 10 to the negative 4 power. Enter. 3.602059991. One decimal place would be significant in this. Because if you remember those, do y'all remember those little test strips that you used? You dipped them in there and then you had to wait for it to change colors. And then you had the little scale on the side of the bottle and you had to try to figure out. It was only one decimal place that you had on there that you could get. You could guesstimate out. So pH level is 3.6. Trying to remember my rules. Closer it was to 0, the more acidic it was. And the closer it is to 7, or closer it is to 10, was more basic. Is that right? Or was it the other way around? Reverse way, where 0 is basic, 10 is acidic. Is that right? There you go. Okay. So I couldn't remember those rules. I don't ever do that stuff anymore. So, and I'm on the other end of the building from the chemistry lab, so I don't get to play in the chemistry stuff anymore. So, no fun. All right. So here's the tougher problem in this set: is if the pH is equal to 7.1, find the concentration of H3O. So this is where we got to solve an equation, where we wanted to get to the whole night, solving some equations. So we set up this equation. 7.1 is equal to the negative log of the concentration of H3O on. Well, pretend that's like an X, log of X. Remember that's log base 10. That's handy to know. What I would do here is that's like a negative 1 that's sitting in front of that, right? Get rid of it. That's negative 7.1 equals log base 10 of the concentration of H3O. Positive ion. Okay? Now, to solve this, we've got to do the inverse of that. So we got to think about rewriting that as an exponential. That's really what we're doing here. Now remember that's log base 10. So it'd be 10 to the negative 7.1 equals the concentration of H3o. Here's an application of all that junk we did back in the about an hour ago, hour and a half ago, maybe. No, it's about an hour ago. Hey, that's our variable. The concentration of H3o is what we're looking for. It's 10 to the negative 7.1. Can I do that with the calculator? I think I can. Ten raised to the negative 7.1. Hey, it wrote my answer in scientific notation. It didn't tell me that's what it was, but it's what it is. This E here stands for the times 10 to the exponent afterwards. So let's go 7.9 times 10 to the negative 8. Is the concentration of that particular ion in our work there. There's an example of solving an equation. It's an application of it. It's a very simple application. That's what we're working with right now. We're going to get to more advanced levels in the next section. That was a simple one. Numbers are not too great. If they were easier numbers, not so many decimals, it'd be a little easier. It'd seem easier anyway. Not any harder. It took one step, really, to 2 steps. If you count the dividing by -1, I don't really count that as a step. My 5-year-old could do that. So, not the log part, but the divide by -1. Yeah, he can figure that out. All right. If he could see it through his pink eye. All right. I love bringing up the pink eye. All right. Example C. We're going to evaluate again. We're going to go through this natural log idea. Natural log of 142. We're going to evaluate that with the calculator. Natural log has its own button. We don't have to do any work to do anything. We're just doing natural log, 142. Let's go 4 decimal places there. So 4.9558. Yay, that's easy. Here's a neat one. Natural log of e to the 3rd. I can do that without a calculator, actually, but to do it with calculators, even neater. So you hit the natural log button. To get the E, you press second natural log. Second natural log. And then put your exponent on it. I bet the answer is 3. It is. The reason is E and natural log are inverses of one another. So it's like saying 1/2 times 2. They cancel each other out. That's what's happening there. The E and the natural log cancel each other out. So it's just that exponent left there. But, you can evaluate that with a calculator if you need to. That helps you out. Let's do one more like we did before. Let's do log base 2 of 6. Evaluate that. We should already know. We've already done one like that. So y'all figured that one out. Four decimal places. You get it, call it out. No. So if we're rounding to 4 decimal places, after the 9 is a 6. So it should be 50. So plethora of ways to do that. You can hit math, go to log base, and type in the 2 and the 6 and hit enter, and you get this number. What I'm saying is this 6 makes the 9 go up, so it becomes a 10, and that makes the 4 go up to a 5. So if you're rounding, that always seemed like such an easy thing to do, but I've found that over the last probably 5 years, it's becoming a less known thing of how to do it correctly. Yeah, I don't know why it's gotten less and less known. I don't know if there's some reason for that, but it seems like when I first started teaching, kids knew how to round. As we progressed through the last several years, they don't know how to round anymore. I don't know where that they're losing that at, but that's it. So there's one way to do it. Another way would be natural log of 6 divided by natural log of 2. And I didn't put parentheses in there correctly, so I got to redo it. Or I could do log of 6 divided by log of 2. That's those, ways you get the same answer no matter which way you do it. Okay, so whichever way you prefer to evaluate it. If you're evaluating with the calculator, those are the ways that you can do that. Get the same answer either way. All right, so pretty easy stuff in section 4.4. Okay, let's go to 4.5 and solve some equations. Fun stuff. This is actually where we're gonna spend some time. All right, 4.5. Exponential and logarithmic equations. Exponential and logarithmic equations. Just kind of got to mix it all together here and see how we got to do this. All right, so methods for solving are kind of going to be dependent upon each problem. Each one can be done a little bit differently. I'm going to try to lead you to the way that works most often. Okay, and try to use that method. That's what your textbook tends to do, and I think will help you maybe as we go along here. All right, so we got several examples of this, and once we get through this, I think we'll be done for the night. Yeah, actually we will. All right, so let's start with this one. 8 to the x power is equal to 21. That is an exponential equation. And normally, I would try to get the bases the same on each side. I know that I could rewrite 8 as 2 to the third power, and I have 2 to the 3x. But 21 doesn't work that way. If that were 16 on that side, if that were 32 on that side, if it were 64 on that side, 256, lots of numbers that would work on that side, but that one doesn't. 21 doesn't work that way. So this is one of those where the logarithms are going to come into play in solving it. Okay? And those properties of logs can help us solve it. And what we want to do is take the log of each side. It doesn't matter what log you use here. There's different ones that you can use and still get the same answer. I'm going to use the natural log because that's what your textbook tends to use the most, and that's the one that we'll use the most for this class, just because that's your textbook style of doing it. And I don't want to confuse. If you needed to go back to that and look at it, then I don't want you to get confused and say, hey, they use natural log and we didn't use that at all, because it can be done different ways. So I'm going to use the natural log. So what I would do here is I would take the natural log of each side. And we know that natural log of 21 is a number. Okay? I'm not going to write that decimal number out. I want an exact answer and a decimal approximation. So we're going to get both answers here. What we want to do here, though, is use the properties of logs to help us out. Look at the left side. What property could I use to get that exponent out of there? Power rule. That's going to bring this x down to the front so that it's x times the natural log of 8 is equal to the natural log of 21. Well, natural log of 8 is just a number. that I could type into the calculator, right? It's a big, it's an ugly decimal number, but it's a number. And x is the variable I'm trying to get by itself. I wrote the times symbol in between there. We don't write that there. I wrote it there so that we could recognize, hey, that's x times a number. How do I get x by itself? Divide by the number that's multiplied by it, right? You know, if we had this problem, 7x equals 14, how would I get x by itself? I divide by the number 7, right? Same idea over here. We're dividing by the natural log of 8. It's a number. It'll cancel itself out on that side and get you x equals natural log of 21 over natural log of 8. And we can get a decimal approximation for that using our calculator that we paid $100 for. So natural log of 21 divided by natural log of 8. Make sure you close those parentheses on that natural log of 21. And we're going, let's see, I think we're doing 3 decimal places on this one. Okay. 1.464. So our answer, there's an exact answer and a decimal approximation for that. But if you use regular log base 10, it gets the exact same answer. If I had used log base 8, I would end up with log base 8 of 21 divided by log base 8 of 8, and I still get the same answer. Okay, there's a lot of different ways. Natural log is the way we're going to do it most of the time on this section, and that works just as nicely as any of the other ways. So if you just use natural log, you're good. Okay, that keeps it from getting so confusing as to which log do I use. I don't know. Natural log is the one you want to use. All right, so let's look at this one. Let's say we had 11 to the x power is equal to 32. Very similar problem. So we should have a better idea about what to do here. I know that 32 is not 11 squared or 11 to a power very nicely. But I got 11 to the x power on the left side. So how can I get that variable out of the exponent? How do I do that? I got to take the natural log of each side, right? And that'll bring it down to the front. And then I do what? Divide by the ln of 11. So natural log of 32 divided by natural log of 11. And let's go 3 decimal places again. 1.445. Exact answer is the natural log of 32 divided by natural log of 11. Decimal approximation 1.445. So far, not too bad. Let's make it more fun. All right. See if I can get one that's not quite as bad as that one first. Let's just go ahead and bite the bullet. 5 to the 2x minus 3 is equal to 8 to the x plus 1. A little uglier, a lot more variables. Numbers are not as big. Maybe that's a good thing. All right. So we got some exponent stuff happening here. How can I get those exponents? They got variables in them. I need to get them down out of the exponent world. Take the natural log of each side. Good job. So the natural log allows that to be 2x minus 3 times the natural log of 5. And this to be x plus 1 times the natural log of 8. E. Only problem with that is the fact that it's two things in the front there instead of just one. So dividing by natural log, it may not help me too much.
Would you subtract one exponent from the other?
Can't do that because they're multiplied to the other things. So what do we remember that this is? Natural log of 5. What is it? A number. And when a number is outside the parentheses here, what can be done? Like if this was just a number 4, I could do distributive property, right? I can still do that with a natural log. Even though it's ugly, it's just a number. So that's what I'm going to need to do both sides.
Would you distribute log into the 2x minus 3?
I'm going to distribute natural log of 5 into the 2x minus 3. Okay? Seems like a long way about it, but that's how we got to get there. So we're going to distribute this to both things. We're going to distribute this to both of them. All right. So that's 2x ln of 5 minus 3 ln of 5 equals x ln of 8 plus 1 ln of 8. Now, when you're solving an equation, what things need to come together? Like terms. Okay, what like terms do we have? Was ln of 5 is it a term? Think about what kind of terms we want to put together. What are we trying to solve for?
Like the 2x and the x?
Yeah, the 2x and the x are the things that need to come together, right? And then the things that don't have an x, they need to come together, right? So that's what we want to try to do. We want to separate them by the equal sign. So we're going to subtract x ln of 8. And we're going to add 3 ln of 5. And they're kind of like terms, but they're not really alike enough that we can really join them together. So this left side is just going to be 2x ln of 5. I don't know why I wrote that. 2x ln of 5 minus x ln of 8. And on the right side, we got the ln of 8 plus 3 ln of 5. Okay, so here, this is canceling over here. This is canceling over there. So that's how we see that happen. Okay, it's a pretty difficult problem. I'm not going to pull, try to put sprinkles on it or anything, make you think it's nice. It's not.
So like all you do is just get them on the same side of the equal sign. You don't have to, like,
Yeah, I can't put them together because one of them's natural log of 5, one's natural log of 8. If they had the same natural log, I could put them together. But since they don't, I can't. All right? All right. Now, on the left side, what's the common factor? Both of those pieces have a what? They have an x. So I could factor an x out. And have 2 natural log of 5 minus natural log of 8. And now, what's all of this? In general, what is it? All the stuff in parentheses. A what? It's just a number. It's not a very pretty number, but it's a number. Okay? So, it's times x. So how can I get x by itself? Divide by the number. Just like we did, if it was 7x equals 14, you divide by the number 7. Here, this is something x is equal to something. We divide by this something and get x by itself. All those are just numbers. They're not pretty. Yeah, I factored it out of the left side. They had a common factor of an x, and that allowed me to get it out there by itself. And then I need to divide both sides by that x, or by that number that's with x. This side, that leaves x by itself. That's what we want. Yeehaw, I've done something right in my life. On the other side, we're just going to have to work this out and divide it. No, because it's tied to the plus or minus stuff up there, so they couldn't just cancel each other out. We just need to get a decimal approximation for that. So, parentheses, natural log of 8 plus 3 natural log of 5, close the parentheses, divided by parentheses 2 natural log of 5 minus natural log of 8, close parentheses twice. So that's what I had written there, and I'm going to divide that and get the decimal approximation for it to 3 decimal places. Should be 6 point something. Yeah, 6.062. That is really as bad as they get. And and that was pretty bad. Process-wise, you gotta think. Okay, I gotta get the exponent down, distribute, get the x's together, get the things that are not x's on the other side, and then go from factoring and going from there. All right. Let's look at an exponential problem. Maybe get a little something similar, but real easier maybe. That one's pretty heavy lifting. I don't know. Example D. E to the absolute value of x is equal to 50. So the base is an E here. That doesn't change what we're doing. It still makes it. It actually makes this one easier since the base is E. The work we're doing is exactly the same. What are we going to do to get the x out of the numerator? I mean, out of the exponent world. Take the natural log. So that's absolute value of x, natural log of E equals natural log of 50. And then what are we going to do? Yeah. That's right. So we have the absolute value of x is equal to natural log of 50 divided by natural log of E. And it's an absolute value problem. Yes. Perfect. Well, I'm glad somebody remembered that. That's awesome. Makes me feel like I did something in Math 100. So positive, natural log of 50 over natural log of E. Negative, natural log of 50 over natural log of E. Natural log of 50 divided by natural log of E. And just FYI, you need to put that in as E to the first power. Yeah. Well, natural log of E is really 1. So the shortcut is you don't even have to do that. You just do natural log of 50. But when you use E on your calculator, it's expecting an exponent for you to use. If it's just E, you use E to the first power. If it was E squared, you'd use E squared. It has to have an exponent there for your calculator to be able to use that E. So that's.
So what is this other one like over this? I mean, I have another one. I don't know if that's on the gestation.
Over the division symbol. That's E to the first power. That's what you could use it. Yeah. I didn't even think about using that one. Yeah. That's what E to the first power is. So you could use that. Yeah. Good looking out. All right. So what was that? Decimal 3.912. And then negative 3.912. That one's had a little twist in it, but it's pretty easy. far as math goes. All right. Get another one. Let's do something with an E here, because it's example E. So you should do problems with the E's. This is a fun one. So we got to remember some exponent rules before we get started. Why would I add them together? Very good. Absolutely. That's multiplication. So it's got the same base. So we need to combine those two into e to the 5x minus 1 equals 5e. And now we can do it like we've done the others. Ooh, we could do that. Yeah, let's go ahead. We'll have to do something else, but it's okay. So that's going to be 5x minus 1, natural log of e, equals natural log of 5e. Here's the problem, is I got a 5e in there, and I really don't need to have that in there. I could leave it because e's a number. It'd probably be okay. Let's just leave it in there. It's okay.
Why would you know?
I guess it really doesn't matter because e's a number. If it were a variable, then we couldn't leave it in there. We'd have to do something else. But since e's a number, it'll be okay. All right. So now with this one, do I have to distribute the ln of e? Why not? Yeah, and because we don't have an x on that side. On the one we did earlier, we had a variable on both sides. This one, we don't have variables on both sides. We just got the e over there, and that's okay. So we don't have to do all of that hard work on this one because there's only variables on one side. So we just divide by the natural log of e. I'll remember that's 1. That's just 5x minus 1, natural log of 5e. And technically, it's over natural log of e. And then it's just simple solving of an equation to get x by itself on this one. So I'd add 1 and divide it by 5. And we're going to get the decimal approximation of that. So natural log 5e close parentheses divided by 5 plus 1 divided by 5. Right? Yeah, it's plus. And in 3 decimal places would be 0.722. Works just fine. This is really equal to 1. The ln of e is just 1. Natural log of e is 1. So I just didn't write it again because it didn't matter. If you evaluate ln of e, you'll get 1. So it cancels itself out. All right, so everything we've done so far didn't have a log in it to begin with. We put them in it to solve them. Okay, so let's look at some problems where we've got a log in the problem. We got to get rid of the log to solve a problem. So let's start with example F. Natural log, or 4 natural log of x is equal to 36. Okay. and see what we can do with that. All right, so I want to try to get x by itself. So I want to move anything that's going to in the way of getting x by itself. So what's in the way of getting x by itself first? 4 and the natural log. How could I get rid of the 4? I could just divide, yeah. That'd give me natural log of x is equal to 9. And then here's what we can think about. How can I rewrite that log statement as an exponential statement? What base is that? Nope. E. E to the 9th is equal to x. Hey, and x is already by itself. I don't even have to do any more work other than just get my decimal approximation for that. So x equals e to the 9th and approximately second natural log. Change that to 9. 8,103, and we'll go 3 decimal places, 0.084. 8103.084. That wasn't too bad. All right, let's say we had log base 3 of x plus 6 is equal to 5. Looks like a very, very small problem. It's small, not too bad. Now, again, you got a log problem. There's only a log on one side. If there are logs on both sides, then we've got to think differently. But if there's only a log on one side, then we want to think, okay, how can I take that and rewrite it as an exponential? As an exponential, what's that rewritten as? Yeah. 3 to the 5th power is equal to x plus 6. Good job. What's 3 to the 5th power? 243. That's just a number. Now I can get x by itself, right? Yeah. 237. Okay. That's not bad. That's pretty easy. Let's do log base 2 of x plus 4 squared is equal to 24. So here's where you look at it and you say, okay, there's a log on one side. Is there anything I can do to make that log a little simpler? So this is where we're using some of those rules for our little cheat sheet here. What rule? Power rule. Yeah, there's a power rule there. There's an exponent on that left side, so I can move that down. It's always easier to multiply by 2 than it is to square something, right? Think about which one you learned how to do first. You learned how to multiply by 2 when you were in maybe 2nd grade. Yeah, it's a lot easier to multiply by 2 than it is to square something, especially if you're squaring x plus 4. So that's the reason we want to do this. Make it easier on ourselves. So 2 comes down. So that's 2 times log base, not natural log, but log base 2 of x plus 4 is equal to 24. And then how can I get rid of that 2? Because remember, I'm trying to get x by itself, so that 2's in the way. I can divide by it. Because dividing by 2 is pretty easy. It's taking half of something. Half of 24 is 12. Now, again, now we have a log on one side, a plain number on the other. We can rewrite that as a what? As an exponential statement. X plus 4 is equal to 2 to the 12th. How much is 2 to the 12th? 4,096. Subtract 4. 4,092. Pretty smart looking problem, not too hard to solve, right? All right. Let's go with this one. Log 2x plus 1 plus log x equals log of x plus 8. All right. A lot going on with this one. There's 3 logs in the road, so we got to fix some stuff, especially that side on the left where there's a plus sign between the 2 logs. How do I put them together? Addition condenses to multiplication. So this side condenses down to log of x times 2x plus 1. This side is log of x plus 8. So the left side is log of 2x squared plus x. The right side is log of x plus 8. If 2 logs are equal to one another, then what they're taking the log of should be what? Equal. So they can cancel one another out. So we end up with 2x squared plus x is equal to x plus 8. And we need to solve that. It's got an x squared in it. So that means what about my solving? I got to get it equal to what? 0. So these the x's cancel, and I get 2x squared minus 8 equals 0. And I get options to solve that. Factoring is one of them. I can divide everybody by 2. That'll give me x squared minus 4 is equal to 0. And x squared minus 4 factors as good job. And then I set those equal to 0. And x equals 2, x equals negative 2. What do I need to do with those answers? Plug them in and check them. Going back to the original, what kind of numbers can I not take the log of? Negative numbers. That's only because I can never. We're dealing with log base what at the top at the original problem? It's log base 10. I can't take 10 and raise it to an exponent and make it turn into a negative number. That's the reason I can't take a log of a negative. So at the original problem, if I put a negative 2 in right here, that's automatically taking the log of a negative. You can't do that. So that means the negative 2 gets thrown out. So x equals 2 is the only answer we have. 2 does work in that one if you go back and plug them in. All right. Log base 3, 4x plus 1 minus log base 3 of x plus 1 equals 3. Got 2 logs on the left side with a minus between them. It turns into division. So it turns into log base 3 of good. That's supposed to be a negative 3 there, guys. Sorry. Make Make that a negative 3. Now what? I got a log on one side, no log on the other side. So I rewrite it as a exponential. So it's 4x plus 1 over x plus 1 is equal to what? 3 to the negative third. What is 3 to the negative third? As a fraction. 1 over 26. Good job. How do I solve that problem? Okay. Here's a better way. It's a fraction on both sides, right? Cross multiply. That'll keep us from having to deal with fractions as much. What you said would work, but we may have to deal with fractions too much. So if I multiply by 27 on that side, that'd be x plus 1 on this side. 27 times 4, 80, and 28 is 108. X plus 27. Now what? Move like terms together. X is on one side, numbers on the other. Times x, that's 107x times 27. X is negative 26 over 107. And then we need to check that. Does that turn into a negative in either of the logs? So what's 4 times negative 26 over 1 over 7 plus 1? That's a positive number. And then 1 plus negative 26 over 107 is a positive number. That actually works. It's a negative answer, but it checks in the problem. Holy smokes. Sometimes. Got 2 more. We're done. Okay. Just 2. Okay. Yeah, I promise. Just 2 more. All right. What letter are we on? K. Log base 2. 2x minus 5 plus log base 2 x minus 3 equals 3. What happens on the left side? Well, it turns into multiplication. Good. You guys are seeing that really well. So it's 2x minus 5 times x minus 3. So I multiply those together. It'd be 2x squared minus 6x minus 5x plus 15. So that'd be log base 2, 2x squared minus 11x plus 15 equal to 3. Okay. Now what? I got to get rid of the log first. So it turns into an exponential. So it's that big ugly quadratic equal to what? 2 to the third, which is 8. 2 times 2 times 2 is 8. Okay. Now I get it equal to what? 0. 2x squared minus 11x plus 7 is equal to 0. Multiply to be 14 and add to be negative 11. I don't think there's anything that does that. If it won't factor, what's my method for solving? Quadratic formula. X equals negative b plus or minus the square root b squared minus 4 times a times c over 2a. 11 plus or minus 121 minus 28 times 2 is 56. It's 11 plus or minus the square root of 121 minus 50. Be 81 minus 6. Be 65. Yeah. Over 4. And if I tried to break down 65, just to simplify, that's 5 and 13. It doesn't go anywhere. I would need to check both of those in the original problem, make sure that it didn't turn negative. If I got a decimal approximation for 11 plus the square root of 65 over 4, 11 plus the square root of 65 divided by 4, 4.77, and then the minus side is 0.73. So I would check those rounded decimals there in the original to try and see if one of them turned negative. The 0.73 does, because when you plug that into the 2x minus 5 or the x minus 3, that gets a negative answer. So this one's out. So it's only this answer, because you can't take the log of a negative number. All right, let's talk about a quick application problem for these types of problems. There's a formula for continuous interest. This is continuous interest. If you're dealing with continuous interest, it's the account worth is equal to your principal investment times e to the interest rate times time in years. Okay, so this is principal. That's your rate. That's time in years. Okay. You don't even have to read this example to do the problem. So it's page 452, example 2. That's where I'm pulling all this information from. Basically, what it says is it's 3% interest. How long will it take to double an investment? But they don't tell you how much the investment is. Doesn't matter. That's exactly right. It doesn't matter how what your original investment is. We're trying to double it. Okay, so we're taking that formula and we're plugging in things that we know. We know we're going to take whatever our principal investment is and we're going to double it at an interest rate of 3%, but we don't know how much time. Okay. If I divide by the principal investment, that's just going to give me 2 equals E to the 0.03 t. That just turns into an exponential equation that we can solve. How did we solve these just a little bit ago? To get the variable out of the exponent, what do? Yeah, we want to use the natural log of each side. So if I take the natural log of each side, that's going to give me a natural log of 2 over here, is equal to 0.03 t. And then what's the natural log of e? Does it turn into? 1 every time. So it really just cancels out. And now I've got a pretty easy equation to get t by itself. I just divide by 0.3 or 0.03. Be a big difference there, wouldn't it? Natural log of 2 divided by 0.03. So I would go to my calculator and type in natural log of 2 divided 0.03. 23.10 years. To double an investment. So if you put $100 in there, in 23 years you'd have $200 at 3% interest. That's not very much. If you put $10,000 in there in 23 years, you'd have $20,000 without doing one thing, just leaving it there. That what they're assuming here is that you're not putting any other money into the account. You're just saying, okay, I got that money, I put it over there, and I'm gonna leave it alone, and I'm gonna forget about it for 23 years, and then, yay, I remember I got some money in the bank. 23 years later, you're like, I'm buying that guitar. That's mine. And going from there. So there's some application of that that'll help you along. Practice problems that you might want to look at. The entire section 4.6 is application problems similar to that. They give you the equation to start off with, and then you plug in the stuff that you know and solve it. It's just but makes an equation out of it. So on page 422, 1 through 99, page 434, 1 through 97, page 446, 1 through 105, page 457, 1 through 51. Those there. You'll have a Canvas quiz that'll come up. Hopefully before I leave here tonight, I'm gonna stay and do a little work before I go home. And then next week we got a test, right? That's not your notebook. That's your notebook. The 27th, yeah. And I just dropped a piece of paper. So, yeah, next week, test. We got some labs to do before the test, and then we'll have our exam, and it'll be one more exam after that, and we're out of here forever. Yeah. You guys have a great week. Email me if you got questions.